When this model came about to be, 1877, this is 1877. We don't have much information about how, for example, we don't have much information about genetics at all actually. One of the things that people were interested is do taller people give birth to taller children? And what was noticed, however, is what's very famously now called regression to the mean, that taller parents might have taller kids, but it's not a strictly increasing relationship, right? Otherwise, our heights would always be on an increasing function. They do have taller kids, but it regresses overall to the mean, which is there are certain mean distribution of the heights around which the observations that we have, even for taller kids, hover around that area, and that's where this term regression was first used in this context. So the idea behind regression is very, very simple. You want to learn the relationship between two variables, and the simplest relationship, right? So in this course, this is a very simple course. We do very, very simple things, right? Not complicated stuff at all. The simplest thing that you can think about is linear regression, where the idea is to be able to estimate the relationship between the parameters. That's the important part. Between independent and dependent variable, right? So you'll just spend 2 minutes or 30 seconds on this particular definition. Is the relationship between the parameters estimating the relationship between independent and dependent variable is linear. Okay, so let me write down certain functions. This is one of the things we will only do in the class because people don't want to come to class anymore, so they should be able to learn on their own, which is great. Okay. So we have first model as y equal to ax plus b. We have a different model, should have revealed it one by one, but we have a different model, ax square plus b. Let's take it one by one. Let's stop it here. Which of these model is a linear model based on the definition that you just saw? Is this? Okay, this is a linear model. What about this one? I will flash the definition again. Relationship between the parameters estimating the relationship between independent and dependent variables is linear. So whenever I write y and x, right? So x by definition is independent, y is dependent, and everything else that you're seeing here is a parameter. It's a parameter that we don't know. We observe this, and we hypothesize that this is a function of this, and this is one of the possible functions that it can follow. In order to actually fix your observations to the data, we will have to tune it, and to tune we require these parameters, right? So these are like the knobs that you have to adjust so that your data that you're seeing here can become a function of x. And the definition is that a model is a simple linear regression if it is the relationship between the parameters estimating the relationship between independent and dependent variable is linear. Right? So this is linear in that definition. Why? Because there is no non-linearity in terms of the parameters of this particular. What about this one? It is also linear. Why? Yeah, so the parameters have not changed, right? And if you want a convincing argument to think about why this is a linear model, since I'm observing x squared, right? I'm observing x squared, I can write this as z or some z. And now my z becomes the independent variable because if x is independent, x squared is also independent, and y can be a function of z. Okay? So this is a z plus b, which is linear in terms of the parameters. How about this one? This is not linear, right? So this is not your traditional, or it could be also x times maybe alpha or beta, whatever. It's not linear. irrespective of that, because any parameter cannot be written as a linear combination of the other parameters. That is another way to think about it. That if I have to, for example, write here B, I will be able to write in the first model, I will be able to write this is what it is. However, in this case, there is non-linearity that comes because of how B is a non-linear function of A in some sense. In other words, there is no linearity in terms of the parameters that you observe. Is that distinction clear? Yeah.
So this product of A and B will not be constant throughout the beta constant.
No, so that's what you have to estimate. And this is a very hypothetical model, but so of course, in what you are saying does not will depend on this factor. I could have just add an x here and make it x square if that is what you're asking. So yes, A and B will have to vary because those are parameters will change. But even if they were not to vary and they were fixed, though in order to estimate those, it becomes super hard in this kind of thing.
Independently you can estimate, but the product can be estimated.
The product can be estimated, exactly, right? Because that will become x plus z, but the parameters are still two. In this case, if I write x squared to z, it's still one variable, because if I know this, I know this, but that is not the setting in this particular case. Okay? Okay, so that's what it says at the bottom. For a model to be linear, the weights of or the parameters should be a linear combination of yi or your variables that you have, where wi is what can be any particular variable that you're learning for this particular observation. That part is clear. Why a model is a linear model. Let's do one more example. What about y equal to what about this one? Is this? It's linear. You see exponential terms there, but that is not going to scare me because I can again write this as z or z, and y is z beta plus c. Okay. What about this one? It is also linear. Anyone? Any other response? Non-linear. Why? Yeah, so variable is exponential, right? So it's not, it's something which if I wanted to estimate what is beta, I will have to do this. Which cannot be written in this form. That's why it's non-linear. Okay? I'm just applying the definition, I'm not innovating anything, I'm not doing anything. Is that part clear? Okay, so if somebody asks you in the next quiz, you will be able to answer this question, right? Okay, any other questions? I'll have to cut this part. Okay, so the best fit line, we have all seen this in some version or the other. Given observations xi and yi in ordinary least squares, we try to estimate the parameters beta. So y is a function of beta. The simplest model, for example, is beta on x. Is to minimize we have to, in order to fit or in order to learn what these parameters are, we have to come up with a loss function. This loss is, so I posited that this is what the model that I'm going to fit, but I don't know what is this and I don't know what is this. What I know and what I can measure is x and y. So in order to learn these parameters, we try to come up with a loss function. We try to measure that how best can I fit my y given my x, given this is a model. So you've already made a choice of a model and then you're going to learn these parameters. There are two possible ways to actually think about how will we learn what is beta naught and beta 1. And we will just do both of them from a very, very surface level. This is again to give you an intuition that when you run regression, in modern worlds, again you will use R, Python, Julia, whichever language you want to learn these parameters, but intuitively what is happening inside when you run this, that's what we're going to see right now. Right. So then in the first setting where we can think of this as a best fit line. It's let's take this example, right? So if you're given this particular kind of a distribution and somebody has drawn this line, how would you think about drawing a line from this data? When you do linear regression, which I'm assuming all of you have done one version of it, what is it that we're trying to really do? What is the goal of this exercise?
Minimize the loss.
Which is what? How is the loss defined in this sense?
In this case, in the linear regression, we can write mx plus c minus y cap.
Okay, so let's
Whole square.
so this is fixed. This is fixed. These are I means ith observation. Okay, now
For the loss, L equals mx.
so I have to learn this and I have to learn this.
Yeah.
Mhm.
L equals to mx plus c minus y actual truth value. It's whole square MSM.
Okay.
So y.
Mhm.
So loss equals to yi minus y cap. That is predicted minus the actual truth. It's whole square.
Okay. Fair enough. So this is what you're observing. This is what your model is. So when you predict, you write this as a hat value generally. Again, the notations here don't matter, but this is the actual observed. So this is OBS and this is predicted. And essentially what you're trying to do in one of the approaches is you're trying to say that, here I have a model, I can predict what the value of yi should be given somebody gave me m and c, and I want to make these values as close to the actual observed value as possible. So that is the mathematical part, and we can run some optimization, and that's how we'll figure out m and c, right? So we'll see what that optimization is in just a bit. But intuitively, when you fit a line, what is it that you're trying to do?
It should pass through the mean of the value.
So it should pass through mean of what?
The distribution, you can say. So x bar.
So what is the mean here? So this is x, this is y. What is the mean?
So for all the coordinates x1, y1, if I calculate the mean of the distribution, say x1 bar, y1 bar, the linear regression should be passing through it. It's one of the point it should be passing through.
So how do I calculate the mean of one point? So this is 1 point, for example.
Yeah, yeah.
Mhm.
So say x1, y1 that is, and let's say another we have x2, y2, and so for all the distributions of x, we can run like summation of x by n.
All summations of x by n. So you mean for the so sigma xi is x bar. Okay.
Yeah.
So
it should be passing through the mean of the distribution. That is the.
But what distribution of what?
These data points.
So
Scattered data points. It should be passing through the hypothetical mean of this. Like if we can get the mean of the entire plotting,
okay.
it should be the linear regression should be passing through the mean of the distribution.
Okay. So how would that? Yeah.
So if we are going to plot the mean of y, x is independent and observations we have and we have a mean of that, will be of that line.
I think he's trying to say something slightly different. You want to draw it?
Yeah. So let's say a line passing through the equation of a line passing.
Show. Okay.
So we calculate similarly. We calculate the y bar.
Okay.
So we take a coordinate x bar, y bar, and that should be passing through.
So let's say.
Could you repeat what you asked?
My question that I asked is, well, I've already asked you this question, but in the interview. But the question that I asked is, when I fit this line, how do I figure out how should I, like in terms of intuitively, at what points should this pass through? Why is it this line the best fit line, and why is it not intuitively? Standard deviation.
So one thing is that it is minimizing the loss.
Correct. That is the mathematical definition, right? So let's take a hypothetical scenario, right? You're saying that x bar. So we'll stick to that. So let's say we are taking x bar and y bar, and what if I invert my y and x? Will that line, or will the parameters that I was calculating? So y is this is my original, right? Which means that x is y minus c by m, which means it's 1 by my y minus c by m. Now in this case, this is my x and this is my y, so I'm hypothesizing a new model here. This calling is beta naught prime plus beta 1 prime y. My question is beta naught equal to 1 by m, and is beta 1 prime equal to minus c by m? Why or why not? Very simple question. This is part is clear, right? I just inverted it. Like simple math, not very hard. X is 1 by m minus c by m. If I fit this line, what I'm saying is no, I don't want to. X is not my independent variable, y is my independent variable. So in this new plot,
So why do you write beta 1 dash y? It should not be beta naught dash y because you took beta naught dash as 1 by m.
oh sorry, yeah. So this is beta 1 dash, and this is beta 1 dash.
Yeah,
Same.
the mean should be satisfying in both the cases.
Same, 100%. You remember the answer?
Yes, sir. So they will not be this.
You remember the answer? And okay, anyone else? You all? Yeah.
So basically, it's what you are trying to predict from what.
Yeah, so there is something special about y in some sense. That's what I'm trying to highlight in essence here, right? Anyone else? You've all seen some version of linear regression, right? Fair enough, so that's fine. That's correct. Usually you will have a sense of independence and dependence, and you will not do this. This is of course a crazy idea. But there is a certain reason why we do this regression in the way that it's done. Because when we are doing these observations, right, there is an inherent assumption that we make is that this is observed. So there is some error possible in my observation. So the usual OLS is your errors in observation model. This could be error prone. Whereas when I'm doing this, I'm saying the error is in my independent variable, and those are not exchangeable, right? So there is some inherent assumption that makes this particular problem special about what is y and what is x. If I flip this, you can always learn these relationships, but it will not be mutually exchangeable. For the other reason that, because when we are trying to fit this line, okay, now let's talk about the actual loss that we are mentioning. Right? So let's say this is your yi, this is your yi hat. The loss that you're maximizing, so this is the point. I can draw a perpendicular from this point to this point. I can also draw a vertical from this point to this line, which is so which of these is y hat and why?
The shortest distance you should
Okay.
if you have to minimize the loss.
Okay.
So in that case, the perpendicular one, base should be.
Okay. So perpendicular is, so you're saying we should minimize this loss. So this is option number 1. Should use a different color. And this is option number 2. Option 2, option 1. Okay. You want to defend?
I will stick to one.
We'll stick to 1. So in linear regression, this is the function that we are optimizing. That's the distance that we are trying to optimize.
For the Euclidean distance, if we take, then option 2 is okay. But if we want to have take the perpendicular distance as the shortest distance, then option 1.
Both of them are Euclidean, right? Like, how does it matter?
Now the thing is that if we want to have like root over x2 minus x1,
It will be a little bit complicated if you go for one. Like, it's not completely wrong, but it will be mathematically much more complicated than.
and what we are optimizing the
Wow,
model.
wonderful. This is this is a best part. Okay, please.
So we are trying to optimize the model here.
Hmm.
So we made a model with linear form of function, and that is giving me an output there, which is coming this not the perpendicular. So performance of model and the data.
Yeah. So I'll summarize it, right? So because we have limited time. So the thing about here, right, is that's why it's very important to understand what is the question that you're asking. Right? What is the simple question that I'm asking? My goal is to be able to predict y. Right? My goal is nothing to do with anything else. I want to be able to have a model with which I can be as close as to what y I should have been. The fitting process of this line is an artifact, or is like a sweet sort of thing that comes out from there. But my goal is that I want to predict it so that my observations is close to the predicted values, and the answer lies in the key there. While you can, of course, we will see this slightly later in the class, when is this useful and when is this useful, but for today's class we'll focus on the second one, which is what the linear regression tries to do. So you always keep missing line socks. So this is the model which is your OLS model. And people who have done, so again, all of you have seen this, right? But this is intuitively, this is what is happening inside the regression setting, is you're trying to say that give me a set of points such that when I get that particular point, it is as close. And the degree of closeness is measured by, why is it vertical? Because there is no error in the independent variable. The independent variable is fixed. So that's why I have to go in this direction, vertical direction. Because I'm saying that what is the yi that I get for an observation that I make, so that I minimize the error that I get. This ball game would have totally changed if I would have also allowed variation to happen in the x-axis. Okay? Make sense? So that is the model that we will work with. Anyone who has idea about in which case you require this?
Sir, SVM.
Going one, no, not a prediction problem. All of you, some of you might have seen it.
Prediction of classes, in that case. Prediction of classes, having a better optimum classifier for these.
Okay, anyone else? Close but not fully close. So this is a way to reduce the dimensionality of your data. Okay. That is how intuitively PCA works, which we'll see in the next class. Okay, coming back to what are the assumptions about any linear regression model. So the first is that there is some sort of linear relationship, and this linear relationship is of course in terms of the parameters and not because of the distribution itself, right? So sometimes you will see that the data looks like this, which means that all you have to do is y is ax squared plus b. So it's you're still fitting. This is called polynomial regression in the regression setting, but in essence it's a linear model because the parameters are linear. It should be independent because the outcome for each individual observations are independent from one another. That is an important assumption. Then normal. There is a normality assumption. If you remember how did normal distribution came about to be, was because somebody was working on the equations for linear regression, and they called a set of equations normal equations because the errors that you get, right? So this is slightly very hard to see now, but when I draw this and when I draw my yi and yi hat, these errors that I'm calculating, these are expected to be normally distributed. The dependent and the independent variables are not assumed to be normally distributed. The errors that you get from that prediction, those are expected to be normally distributed. That is the only assumption that is also important. And there is an inherent assumption of equal variance, which actually fails a lot in other data sets. This is the variance of the residuals. So once I have fit a model, I can calculate. So if my fit model is, sorry, this is messy. If my fit model is y, y I had, I can calculate yi minus y observed I, and this is residual. thing that you were not able to capture by your model. So for example, in this case, where it go? In this case, this is my residue. Okay. The residuals are expected to be to have equal variances, so they follow normal distribution, but that normal distribution's variance should be constant. Does it all make sense? So we will see this intuitive. That's why it's important to see the other way to solve this, right? So very quickly, how is the line fit? We'll see the probabilistic version where it will become slightly more clear. So this is how in your model, in your regression setting, in your R Python retriever toolkit, this is what it's trying to do, is it's trying to find a line which will minimize these errors. So when Shauradeep said that we should minimize the square, this is what we are minimizing. Why square? Why should I minimize square?
Otherwise, if they are equally long in both sides.
Fair enough. So there's no point of minimizing just this value, right? That we all agree with. But I can minimize this value, no?
It will become sparse.
How?
If the thing is that during the regularization process, it always points towards either 0 or 1. Then it becomes very sparse during the back propagation. So to make it very close to 0 but not exactly 0 or 1, so we take the square.
Not there fully. That argument applies in Lasso when you think about what is the right choice of model, but not here. But good attempt. It's close but not fully. Anyone else?
So one advantage.
Yeah.
We want to give higher weight to large errors
Okay.
because the square will like amplify the errors.
Okay. So you want to make lesser observations where you are differing by a lot. You want to emphasize it. Okay.
So if the loss becomes 0 for some reason, then the back propagation won't happen at all. That is, it won't back.
So 90% of this class, including me, I don't know what is back propagation.
So it's good to have differentiable stuff.
Yeah, right. So the very simple definition is like this is that's why I said it's partially correct, and it's kind of close to what you're saying, but not fully. Which is that it's easier to optimize. Like anytime you see square, right? Especially when you have the square assumptions, it's easy to satisfy. I could have been degree 4 also, but degree 4 is complicating it. So best would have been degree 0, which is your usual residual, but we will run into issues there because things will start to subtract each other, and we'll not be able to figure out what is the right line. Because in some cases this is negative error, but this is positive error, which we will mutually cancel out each other, right? Which fit is not, so it's not going to necessarily give you the best fit. So then we would have moved to an absolute value, but absolute value is, I think probably that's what you were also trying to highlight, as hard to sort of work around those settings mathematically. Right, so how do we do it? You don't have to worry about the mathematical derivation of it, but you take partial derivative with respect to m and b, set it to 0, and having a square here is helpful for that reason, that the derivative is very easy to calculate compared to what if it was an absolute value, which would be a nightmare. There is another reason for this. This is not complicated anymore because we have access to algorithms for being able to do differentiation. This is not a complicated problem anymore, but we're talking about 1877. All they had access to was tools, this handwritten tools. That's why they chose squared. Okay, we will just see a linear algebra version of this. Not super important from the exam point of view, but interesting to know about if you deal with this data. So in real world, right, like y equal to mx plus c is something is okay to do it in class, but in real world it will never be y equal to mx plus c. Why? Because you will have multiple different variables. Here I had only one independent variable, well, because I can only draw one, or at max two, to give you an idea about. So my engineering drawing is extremely poor, but if the other version, if there was x variable 1, x variable 2, this is what it would look like. You will have in real world setting where you have multiple different independent variables, which is what these p variables are, right? So in essence, your data would look like this, which is a matrix of covariates. These are independent values. These are the dependent values. Y is dependent on X. There are P of them. P equal to 1 is the case that we did on the board. But if we had multiple of them, then it would become a matrix or a linear algebra problem where we're trying to optimize the same thing, the same function we're trying to optimize. And this coefficient beta hat encompasses the intercept, which is beta naught, but also the slope. So if it is a multivariable regression model, so much time wasted in this walk. Is so any optimal solution for where this should be, honestly? Engineering solution.
In the middle.
Of course, it should be here, right? Like, so y is beta naught plus beta 1 x1. So in this setting is the setting that you're looking at. This will be p equal to 2. That means I have two independent variables. The optimal coefficient of beta 0 becomes like a vector. So this is beta 0, beta 1, beta 2, which is equal to x transpose x inverse x transpose y. Don't have to worry about it so much. It makes sense to know what is happening because that will help us interpret the results. Okay. Now there is another version which I think you were trying to highlight. So one version we saw is we talked about losses and everything, right? We talked about yi minus yi hat, and that is giving us a distribution. When we look at the normal distribution, there are two parameters of it. One is mean and variance. So we will now use this idea to see a different interpretation of what happens when you actually run a regression. Okay, so this is where the idea of the residual, and this is actually the original formulation, part of it is original formulation, is you can imagine your model to look like this, which is yi is equal to mxi plus b plus epsilon I. This is the error that you are obtaining in your observations yi, and this epsilon I is distributed in a normal fashion with a mean of 0 and sigma square. Is that what you were highlighting? And with a particular variance of sigma square. This sigma square is fixed through all the observations that you're going to make. Each point, in a sense, so this gets slightly meta, in the sense that you have to imagine that whatever observation that you're doing here right now, each point is likely a realization of this Gaussian distribution. What you're essentially trying to see is, even though I got this particular point, it itself has a distribution which is normal, because I can assume that if I assume that xi is also normal, which is not required for linear regression, then yi will be normally distributed around this point. And essentially when I'm trying to fit my line through it, I'm trying to learn the line which passes through this mean parameter of all these distribution, of all these residuals that your epsilon. So in a sense, one way to learn this is to not do regression or not do anything to do with squared errors, but to maximize the likelihood. We don't have to worry about it. I'm just giving you intuition. So each point has a probability. We saw that if you have a probability distribution function, the probability gets maximized here. We are trying to essentially learn what are the values of m and x, so that once I observe this data's probability distribution is maximized, or the probability associated with with what probability I can observe this entire data is maximized, which is quantified using the log likelihood function. Since each of the points is normally distributed, if I multiply their probability density functions, I get the probability distribution of the entire data. And in this version of probabilistic regression, I'm essentially trying to look for m and c, which I can learn by what's called maximum likelihood estimation. Don't have to worry about right now. Is how to learn this parameter if this was to be maximized. Okay. So you don't have to worry about equations there, you don't have to worry about derivation. Intuitively what you're trying to do is I'm trying to learn the m and the v such that the probability of observing this data gets maximized, conditioned on the fact that each point is likely realized from a normal distribution. Okay? So you multiply all of them and try to learn what parameter m and b will give me the maximum value, because yi follows that one. Does that make intuitive sense? So this is the probabilistic interpretation of regression. Any questions about this?
If we start thinking like that whatever we are seeing would be resulting from the distribution of pairs.
That's what LLMs do, by the way.
Yeah.
All the modern world, why do LLMs work? The LLM is trying to learn the over all the text that this world has generated, what is the probability distribution of generating something? So my name is X. What is its inherent distribution? So I type certain question, and then it's trying to essentially generate the next set of words based on condition on the fact that I've generated something, because it has learned over multiple different texts what does the distribution look like.
This assumption is making it difficult the first step of assuming the form of function, looking at the data. But then if I see something
Yeah.
looking sinusoidal, it could be that it is linear and it is coming from this where it is coming from.
Yeah, so no, so you will still plot your data. Like, you're not going to get rid of it. The first step has to be that you just plot the relationship between what is the relationship. Is there even a relationship that you would like to model? Right? So this is all conditioned on the fact that you know what you're doing. You know, in a sense that you
The
have.
underlying truth, we know that it is linear, and then we are.
Well, this is again, I'll just quote that famous model that all models are useless, but some models are useful. So this is one particular model which will be useful for you to explain what you're observing, but does not necessarily mean what it's saying. Okay. Okay. All right. We can speed up now. So in R, it's very, very simple, and I think we can do this now in stats models and Python as well. It's very, very simple to fit a line. To fit a line between y and x, all you have to do is lm, linear model, y as a function of x. It's that red line. Linear model, x as a function of y is that green line, and these two lines are different. They're not the same for the reason that we discussed.
So are they passing through the same x bar y bar?
They are passing to the same point in this case because they are mean centered. Yes. Okay? All these observations are mean centered, that's why. Any other questions? Okay. One important thing which often doesn't get discussed is homoscedasticity and heteroscedasticity. So one assumption and key assumption of linear regression is the variance that you see at a particular value of I or any observation is constant, which you see here, right? If I go here, the spread is around here. If I go here, it's the same, and same. Whereas in this case, the spread here is this much, so variance is some quantity y or some quantity sigma square. But if I go here, then the variance is increased. It is heteroscedastic because the observations here have much higher variance but also different variance from what you began with. You should never fit a line in a linear model or a linear regression setting if you see the data like this, because it breaks the assumption of linear assumption, which actually linear model is not designed for. In one or two lectures later, we will do one model which actually accounts for heteroscedasticity. Linear regression, your OLS is not designed for this. So that's why it's very important to look at your data before you fit any line. Okay. Okay. So we have already discussed this. So I'm going to skip what is so special about squares. We have already discussed. If you wanted to do an absolute fit, it would fit a Laplace distribution. Don't worry about the distribution. This is what it looks like. We know certain properties about Laplace, but now in the modern day world, we can calculate these quantities very quick, but we're talking about 1877 when that concept did not exist. The distribution did, but that's why we use squared for historical reasons. So once you have fit a line, you can calculate what are called residuals. And one way to figure out whether you have done the right job is to look at these residuals. These residuals have a lot of information, and this is what again something that you can relate in real life. If you have a model of life and if you see a deviation, that deviation is the residual from what you would have predicted, and there's a lot that you can learn from those residuals. Things don't go well, that's a residual that you should use to get a feedback on. That is what we use to diagnose a fit. Whether, while you can always run a linear regression, the model will not, the software toolkit will not tell you whether you should run it or not. You can always run it. But how to assess whether it's doing the right thing or not? There are 4 different checks. In the first check, what you do is you take these residuals. So this residual for each of these observations, I will take it. I will plot it against my fit values. So essentially what I'm doing is I'm asking, is this quantity a function of y? Why should I ask that?
It's not, it should not have a dependence on this.
There should be no dependence between the residuals. That is how you check it. You take these residuals and you ask a very simple question that if I do a scatter plot of all these residuals as a function of y, is there any relationship? And you expect this to be flat. There is no relationship. So that's a first check that you would do if your model is a good fit or not. The second one is because the assumption is that these residuals are supposed to be normally distributed. That is an underlying assumption of OLS. They should have, if you draw them against on a QQ plot, and now you have seen the QQ plot already, theoretical quantiles on the x-axis, standardized residuals. So you take the residuals, you standardize them, so you put them under, this is not really required, but you can put them in a certain range, and just plot a QQ plot using this. They should be normally distributed, which means that they will fall along on this particular line. Okay? That's the second check. In the third check, what essentially you're trying to do is you're calculating the standardized value of the residuals, and you're seeing if there is any trend between the values that you're getting. The reason to use this standardized residuals is to remove the, or is to sort of dampen the effect of very large residuals. Are they spread evenly along the range of the fitted values, right? So while overall here, you got the idea that there is more or less no trend, but is this spread that you're seeing, is that constant across your y? That's what the scale location plot tells you. In R, this is very easy to do. There's one command to do this, which is you fit the linear model and you just do plot that linear model, and it plots all these 4 things. It will tell you whether it's the right thing that you're doing. And finally, you calculate what's called, again, look at the standardized residuals, but now you calculate a quantity called leverage. Any idea what is leverage? Any idea what is leverage? Otherwise, we'll do an example, very quick example. We'll also do this in your assignment. Oh, by the way, the assignment will likely come out today. It will be due within a week. So it comes out at 5 p.m. It will be due 5 p.m. next Wednesday. It took me slightly longer to streamline it this time, but it should come out today. Yeah. Any idea what is leverage? Use a different. Any idea what is leverage? Leverage. Let's do an example. We'll forget this point for now. If I fit a line, do you agree it would look like this? Okay. What if I added one more point? What would the line look like? It will deviate. Why? It's going to reduce. It is going to contribute a lot if you don't do this, because the yi values is this residual. It's a large value, so it has high leverage. There's somebody in your family who will have high leverage. Whatever they say, you have to follow it, or most of the people will have to follow it. This is that point which can make the line bend. It can make your decisions bend. That's what the high leverage point is about. So you want to essentially understand whether these residuals are there points which have, how does their contribution vary across the overall leverage that you have. There's a calculation for leverage which automatically happens. Will not cover that in the class, but the general idea is intuitively how will you assess whether a point has high leverage or not?
By distributing outliers to check if the number of
Simplest
outliers.
explanation, simplest one.
Box plot to check the outliers.
Okay, you could do box plot, okay, but there are two. What if it's a multiple regression set?
So we can lower the dimension and check if there is any such kind of outliers.
Okay, you could do lower dimension. Okay, anything else you can do?
Residual length.
Residual length. In what sense?
More the length.
Can we do something what we did? I can delete that point. I can delete one point at each time, and I can fit a line again and measure how much does my beta naught or beta 1 deviate. If they don't deviate a lot, if they don't seem to change a lot, my point does not have a leverage, for example, or does not have a high leverage. Even if I delete this, I can tell you that the line that you will get is going to be very, very similar. So its beta naught and beta 1 will be same as beta naught, beta 1 of the original. So that's how, intuitively, that's how leverage is
Is
calculated.
that loop one out?
Yeah, you can drop one of these points out, fit it, and then you can calculate leverage. There is also a direct formula for calculating, which we don't have to talk about. Okay. So this is quantified using Hooke's distance, which is what I was talking about. You don't have to do it, but R does it for you automatically. You can use Hooke's distance to measure whether a point has a high leverage or not. Okay. So what is a good fit and what is a bad fit, right? So case one, of course, is residual versus fitted. It's a flat line almost. Again, all of this is very ballpark, right? I'm not quantifying this number. I'm just ballpark. I'm just eyeballing my data and saying that no relationship. Okay, now I'll flip the question. If you see a relationship like this, can you tell me what the original data looks like? This is residual versus fitted. So this is diagnostics, right? So you have to, while the machine is telling you it's going to stop there. The next step is that for you to figure out what went wrong in your public, this is all public health, right? So somebody's life is at stake. You have got the wrong model. But what went wrong? Like what is possible of, what does the original distribution look like? Louder? So it is heteroscedastic in some sense, yeah. But I'm asking for, that's correct. But I'm asking for the relationship as well. What does Y and X relationship look like? Yes. Okay, so like this. Okay, anyone else?
So it's bulging in between, but in which direction it is not clear. For the case two.
Okay, so let's look at the values. So residual by definition should be close to 0. Well, you know, it's a standard normal distribution. So in between, it's doing a good job. It's there, almost there, flat. Forget about these lines, almost there. But on these sides, something is going wrong. What is going on? So, okay. So in the middle, things are okay, right? Things are okay. This could be possibly the middle. Is that possible? What happens in the extremes? Yeah, it's going to deviate, right? So it's going to be maybe like this, or maybe like this. I don't know. But something of this order. Things are not so bad in the middle, right? So there is some sort of a curve possible. Maybe it is this, maybe it is this, something like that. Could be an S-shaped curve. But the essence is what I'm looking for, or you should look for, is what is happening in the middle, here and here. Okay? Any questions? That's true. It has the same sign. That was actually correct. That's actually a good point. Okay. Then how should I draw it? Okay. So like either like this, something like this. seems slightly weird, but yeah, something like this. So again, an example to take over and maybe do it in the assignment to see what happens. Okay, tell me about this one. So left one is good, of course. Right one, what is happening? QQ plot.
There are many outliers.
Who said? High leverage, okay, high leverage. Outliers. Anyone else? So how should I draw? Like I'm looking for the XY distribution. What could it look like?
So in middle it will be flat and it was from before.
Okay. So something. I think drawing points is better than yeah. Okay, and then towards the lower tail. Is it going wrong in the lower tail or the upper tail? Upper tail, right? So easy to see. So something weird stuff going on there. It's deviating from normality, right? So it's not normal anymore, right? So the residuals could essentially have a much skewed shape, right? So it is also heteroscedastic, but doesn't follow your usual distribution of normality. Okay, one more. Scale location. So standardized residuals, and the one on the right. So on the x-axis is your fitted values. Y-axis is your square root of the standardized residuals. So you have put them on a particular scale, you're taking just the square root of it to see how much spread is there for the residuals at a particular value of x. What is that distribution? Louder. It is heteroscedastic, right? So very easy to see because the variance is, as you have higher values here, the spread is of course increasing of residuals. By definition, they should be constant, which is it is not. Okay, this one is slightly tricky, but not super hard. Left one is okay. What about right one? Residual versus leverage. Leverage is how much influence a point has on the x-axis, and y-axis is just the standard residuals. So what would it look like? You can also see it actually from that plot, what is happening. There's one huge outlier here, which is queuing up all the calculations. Still it is okay, and then it's trying to reach up all the way till. Okay, so usually in the exam, sorry, this is repeated. In the exam, we give similar examples to, sorry, I don't know why when I was copying it, it got copied over. So whenever in the exam we give you some scenarios where what does the alternate data look like. For example, if you're given from the setting, how do you figure out from a linear fit? That you should be able to do. So the residuals in terms of what is happening very briefly in the regression setting is you have learned beta naught and beta 1. We are minimizing the residual sum of squares. Your E1 is yi minus yi hat. This is just a summary of what we did. And your beta 1, once you do this, you can learn what is your beta 1 hat, which is the original slope parameter. And then your beta naught, which is simply the subtraction of that you get after subtracting from the mean value of y, beta 1 times x bar. So that's, you don't have to go into the derivations right now. But why I'm talking about this is what we're going to see now is how to interpret these values, right? So while we have fit everything and so on, which all of us are able to do, there is a reason we are fitting these values, and that's why these equations will now start making more sense. So this equation will be defined, right? This defines your regression line or your population regression line. But of course, you don't have access to the population. We take a sample. the interpretation of beta naught is it is the expected value of y when x is 0, right? It is the expected value of y when x is 0. Beta 1 is the average increase in y for a unit increase in x. That is how you interpret these values. So while they have a meaning, while they have of course a mathematical definition and you can derive them, this is how you interpret them. What does it actually mean? And an epsilon is trying to essentially capture your true relationship between x and y, whether that is linear or not linear. That is your error term that we have, right? So overall, in this essence, what we are trying to do is we are trying to figure out what is the average, what is the overall population line that we try to fit. Beta naught essentially explaining what will be our value of y if x is 0, and beta 1 is how much will y change by if I change x by 1 unit. So in a sense, if you think about this in the setting that if you think about all of this is coming from a large distribution which is generating these values, what we are trying to fit in terms of our estimate line, right? So in this case, if I gave you access to all the data, then you would have fit this population regression line. But of course, you don't have access to it. You have access to only a sample of data, which is what you're trying to do in the best fit version. In this example, what I did is I randomly sampled certain x and y from a large pool of data that I had simulated. And what it is showing you here is, while this is the population line, each sample will result in a different fit. Now, because we are able to derive their properties and we are able to interpret them probabilistically, we can understand that how close is the value of beta 1 to its population thing, to its population corresponding parameter, right? So how would we measure how confident are we that beta 1 is going to be similar if we were to take a different sample of x and y? We studied this in the class.
Standard error.
Yeah, so you also, while beta 1 or beta 0 is one quantity, you also want access to the standard errors which are associated with these parameters to get a sense of, if I were to repeat this experiment on a different sample, how much will my estimate of beta 0 and beta 1 deviate by? Okay. So that brings us to this same discussion that we had, which is what is the difference between standard error and standard deviation. So there's some math here which you don't have to worry about, and I'll not quiz you on this ever in the exam. But if you have access to beta 0 and beta 1, you can calculate the standard errors associated with beta 1 and beta 0. This comes based on the assumption that there are certain distribution assumptions which hold true in general. But very, very briefly, the standard error of beta 0 is a function of your population variance, and the standard error of your beta 1, which is the slope, is also a function of population variance divided by the sample variance of x. Don't worry about these equations at all. I will not ask you this. But does that make sense? That there is a way to calculate these standard errors. So then we will ask about what is a confidence interval. Right? So you would have probably come across this term called 95% confidence interval. So if you run regression in R or Python or any language, first thing that it will give you is, it will give you a column that they estimate, and then it will give you a column of 95% CI. We will not get into the mathematical thing which I just showed you how it is derived, which we will not quiz upon. But let's say it gives you some value, let's say beta naught, and this is some value beta naught minus x and beta naught, let me call it minus c and plus c. What is the interpretation of this 95% confidence?
Getting a particular point, estimated as particular point, say using log likelihood or anything, that induces a certain amount of error because everything is stochastic kind of, everything is not true.
Mm-hmm.
All this. So, but having a range of the data, possibility, so that actually clears out that, say we need to inject this amount of medicine only into that patient, no, we can have this range
Okay.
that varies.
Okay. Let me simplify this a little bit. What is your null hypothesis in a regression set? What is a null hypothesis in a regression? You're doing a regression. What is your null?
It is related linear.
Most
Okay.
likely
No.
this-
What is a null?
Hypothesis as an argument.
What is a null hypothesis when I do a linear regression? What is my null hypothesis? Error is 0. Simple life. Simple. You already chose a model.
So now we are saying that the mean of beta naught is this, we know from somewhere, and then we are trying to reject it.
Okay. So
From there, this confidence is
There is no relationship between x and y.
correct. There is no relationship between x and y. That is your linear assumption, right? So that's why I will just make changes to beta 1 because it's slightly easier to motivate. If I were to quantify this, what? Sorry, forgetting your name. Sahil, yes. What Sahil said. If I were to write this in H naught and HA form, what is it?
Beta 1 equals to 0.
Beta 1 equal to 0. Right? So we are not doing hypothesis testing just out of air. The reason it is discussed before regression is to make sense of what we are going to interpret now. So our assumption is that the simplest null here is there is no relationship between y and x. So beta 1 is 0. And alternate is there is some relationship and I don't care about what it is. This is one way to test it. So similar to what we did in the statistical case, just like our t statistic or any statistic has a distribution, similarly beta 1 has a distribution, and you can calculate whether what is the probability associated with whatever value of beta 1 you get, which is, for example, if I get a very extreme value, let's assume that this is a distribution of beta. If I get an extreme value of beta here, I can reject that null, and that's why for each of these quantities you can also report a p-value, that while you're getting a slope, is that slope statistically significant or not? The 95% confidence interval interpretation is that if I were to repeat this experiment 100 times, 95 out of those 100 times, the sample estimate that I get, this is a point value, this is a point estimate. So if I were to repeat this experiment 100 times with a different sample, around 95% of the time, my value of beta 1 will lie in this interval. And where is this interval coming from? It's not coming from thin air. It utilizes the idea that beta 1 has a distribution, it has a standard error, and 95% and this particular range captures 95% of the time you will see your beta 1. Similarly, there is confidence interval for beta naught as well, right? So we just discussed this. I think we'll have to stop in a minute. But the idea here is, this is all related to hypothesis testing. The simplest hypothesis is there is no relationship. Beta 1 is 0, or the alternative is beta 1 is not equal to 0. We will revisit the statistic. This distribution, beta 1 minus 0. So this is x bar minus y bar divided by the standard error of beta 1. That follows a t distribution. So beta 1 itself has a distribution that it follows, and that's why you can calculate a p-value. So very quickly, I'll just show you what it looks like in the regression setting. Sorry, my slides somehow are repeated. So we'll do a regression example, which actually is missing from this slide, where when you do this output in, actually I can quickly show you this. Sorry, just give me 1 minute. So if you run any linear model in R, I'm going to do it now. So essentially, if I fit a linear model between the sepal length and let's say the sepal width, my linear model is LMX. I can try to print the summary. So if I print the summary, it prints a big table I've simply done a simple linear regression, right? But it prints a big table, and that table tells me what is there in my data, right? So it is telling me that, of course, there is some residual and so on. But here is the thing that I worry about. What is my slope? My slope is 6.52. It has an estimate, but it knows that this also has a distribution. So it is reporting what is the standard error, what is the corresponding p-value, and is that significant or not. Okay? So this is your estimate for the slope, minus 0.22, standard error is 0.551, p-value is minus 1.44, and the p-value is 0.152. What is the take-home message from this fit? Should I do this fit, or does this fit not make sense? There are multiple ways to diagnose it, right? So one is, of course, you can do those diagnostic plots. But here also it's telling you something. So estimate, standard error, t-value, because it follows a t-distribution, and the p-value, which is 0.152 here. What do I do to reject? What do I do? Whether I reject the null or I don't reject the null? I don't reject the null, right? I cannot reject the null, which means that all this exercise of fitting this distribution blindly is not going to pay you a price. While you can fit it, but it does not make statistical sense. Okay, so we'll stop here. We're almost done with regression. In the next class, we pick up with just some small things that we discussed. There's no class, of course, on Friday. We meet next Wednesday. And we will pick up the idea about how to model heteroscedasticity if you have heteroscedastic data. The assignment will come out today. We'll be doing 1 week on